Today, we're going to talk about Earth 2.0 candidates. The search for Earth 2.0 refers to the ongoing quest to discover exoplanets that share key characteristics with our Earth, particularly in terms of size, orbital distance, and potential habitability. This search is driven by the desire to understand the prevalence of habitable planets and the possibility of finding life beyond our solar system. Key aspects of the search: Mission ET, Earth 2.0. A proposed Chinese space mission aims to detect Earth-sized planets orbiting Sun-like stars using a series of wide-field telescopes. Techniques: the search relies on techniques like transit photometry, observing changes in a star's brightness as a planet passes in front of it, and microlensing, detecting gravitational lensing of a distant star by a foreground star. Goals: the search aims to determine the frequency of Earth-like planets, understand how terrestrial planets form and evolve, and potentially identify planets with the potential for life. Target characteristics: researchers are looking for exoplanets that are Earth-sized, located within the habitable zone of their star, the region where liquid water can exist on the surface, and have a nitrogen-oxygen atmosphere like Earth. A superhabitable planet, according to scientists, is one that could potentially host more life than Earth, offering a more optimal environment for biodiversity and biomass. Key criteria for superhabitability include being a bit larger than Earth, orbiting a star of spectral type K, orange dwarf, and potentially having a warmer and moister climate. Here's a more detailed breakdown of the criteria. 1. Size and mass. A planet larger than Earth, potentially by about 10%, could have more habitable land area. A mass about 1.5 times that of Earth would allow for longer-lasting radioactive decay in the planet's interior, providing more heat and helping retain a thicker atmosphere. Planets with a size between 1.2 times Earth's radius and 2 times Earth's mass can potentially retain hydrogen and helium from the protoplanetary disk. 2. Orbital characteristics. Orbiting an orange dwarf. Orange dwarfs, K-type stars, are stable for longer periods than Sun-like stars, G-type, potentially offering a more stable environment for life to evolve and thrive. Circular orbit. A more circular orbit would lead to a more stable and consistent climate, unlike a planet with an elongated orbit that would experience significant temperature fluctuations. 3. Temperature and moisture. Warmer surface temperature. A mean surface temperature slightly warmer than Earth's, around 8 degrees Fahrenheit or 5 degrees Celsius, could lead to larger tropical zones, which are known to foster greater biodiversity on Earth. More moisture. Higher levels of moisture could further enhance the suitability of a planet for life. 4. Other potential criteria. Magnetic field. A strong magnetic field is important for shielding the planet from harmful solar wind and radiation, which can damage the atmosphere and surface. Atmosphere. The atmosphere should be suitable for life, with a composition similar to Earth's, primarily nitrogen and oxygen, and potentially a layer that protects against harmful UV radiation. Liquid water. The presence of liquid water is essential for life as we know it. Gravity. Sufficient gravity is needed to retain an atmosphere and for the planet to maintain a spherical shape. So, what are some candidates for being Earth 2.0 or superhabitable? I found one, Kepler 186f. This one orbits a red dwarf star around 558 light-years from Earth. This is far, but with warp drives, we could reach it in weeks, or even just days. Let me tell you how warp drives work. Warp drives, like in Star Trek, are fictional propulsion systems that allow faster-than-light travel by manipulating space-time itself. They work by creating a warp bubble around a ship, with the space in front of the bubble contracting and the space behind expanding. The ship then moves within this bubble as space is warped around it. Here's a more detailed breakdown. Warp field generation. A powerful energy source, like a warp core, generates high-energy plasma, which is then funneled through warp coils or generators to create a warp field. Warp bubble. This warp field forms a warp bubble around the ship, distorting space-time. Space-time distortion. Inside the bubble, the ship experiences normal space-time, but the bubble itself is moving through space-time faster than light. Traveling at warp speed, the ship is carried along as the space around it is warped, effectively riding the warp wave. Subluminal travel within the bubble. While the ship itself might not be traveling at faster than light speeds relative to the space within the bubble, the entire bubble is moving superluminally. So let's keep talking about Kepler 186f. Kepler 186f is called Earth 2.0 because it's the first Earth-sized exoplanet discovered in the habitable zone of another star. This means it's at a distance from its star where liquid water could exist on its surface, making it a promising candidate for supporting life. Here's why Kepler-186f is considered so Earth-like. Size: it's slightly larger than Earth, with a radius of about 1.1 times Earth's. This suggests it could be a rocky planet, similar to Earth, rather than a gas giant. Location: it orbits a red dwarf star within the habitable zone, where liquid water could be present on its surface. Potential for life: the combination of its size, location, and the possibility of liquid water makes Kepler-186f a strong candidate for harboring life, though more research is needed to confirm this. Stable climate: BBC Sky at Night magazine suggests that Kepler-186f likely has a stable climate with regular seasons, similar to Earth. Unique light: the red dwarf star Kepler-186f orbits is cooler and redder than our Sun, which could lead to a different color palette for plants on Kepler-186f, possibly with red plants instead of green.